Hello everyone, I am Pei Zhang from Tianjin University, a Triple E Fellow. In this micro course, I explain how reinforcement learning can support transient stability control after severe power system faults. The problem is practical. When a disturbance pushes rotor angles apart, operators have only a short time window to shed load, trip generation, or apply other emergency actions. I use this course to connect three ideas: the physical stability criterion, the reinforcement learning decision model, and the engineering evidence from New England test system studies. A useful way to listen is to keep the protection time scale in mind. The algorithm is valuable only if its decision can be computed before rotor angle separation becomes irreversible. That practical limit shapes every modeling choice that follows. The course follows 5 blocks. I begin with the operating background. Because renewable generation and power electronics change both disturbance patterns and control timing, I then formulate emergency control with a deep Q network, or DQN, so the controller can learn an action from measured system states. Rainbow is the third block, where I combine several DQN improvements into a stronger agent. Transfer learning is the fourth block, because training every new fault from zero is expensive. I close by summarizing what reinforcement learning contributes to real-time stability control. The sequence also mirrors a deployment path. I first define the control problem, then choose a learning architecture, then improve training behavior, and finally reduce the cost of adapting the method to new operating conditions and fault locations. The background starts from a tension between physics and timing. A modern grid has high renewable penetration and many power electronic interfaces, so the post-fault trajectory can change quickly and non-linearly. Emergency control means actions such as generator tripping and load shedding that stop the system from losing synchronism. Traditional schemes are often open-loop. A contingency is detected and a pre-designed rule is triggered. Optimization-based emergency control can be accurate and expandable because it explicitly minimizes control cost under stability constraints. Its weakness is computation time. A mathematically optimal answer that arrives after the transient window has closed has little engineering value. In practical operation, the difficulty is not only finding an action, but finding one with enough confidence under changing renewable output, converter controls, and protection delays. That is why a purely offline optimization workflow can struggle when the real system state is moving quickly. Wide area measurement systems change the information side of the problem. Phasor measurement units provide synchronized measurements from generators, substations, transmission corridors, and load areas. Those measurements can feed a control center in milliseconds, which is the right time scale for emergency decisions. The diagram on the left represents measurement, monitoring, analysis, and control as a closed wide area loop. The diagram on the right shows a data-driven workflow. Training data builds a model, input data produces a prediction, and evaluation improves later decisions. My control target is not offline diagnosis. It is a measurement-driven action fast enough to affect the transient. The value of WAMS is the common time reference. If measurements from distant locations cannot be aligned, the controller may compare states that never existed at the same instant. Synchronized phasors make the learned policy act on a coherent snapshot of the grid. I treat emergency control as a Markov decision process. The state is the current power system condition. The action is the control command, and the reward measures whether the command improves stability at an acceptable cost. The Markov property means the next state depends on the current state, not on the complete historical path. That assumption is reasonable when the state vector contains the rotor angles, speeds, voltages, and other variables needed to describe the dynamic condition. The return GT is a discounted sum of future rewards. The state value function and the state action value function express the expected return under a policy. In control language, I am learning which action has the best long-term consequence from a measured operating point. The diagram also clarifies the learning signal. The environment is the simulated or measured power system. The agent does not directly minimize a differential equation. It observes the consequence of actions through reward. That is why reward design is as important as network design. The formulation maps optimal control into reinforcement learning variables. On the left, the objective minimizes emergency control cost from generator and load actions, while constraints keep active power, reactive power, bus voltage, and rotor angle differences within limits. On the right, the state space contains generator rotor angle, generator speed, bus voltage magnitude, and bus voltage angle. The action space contains generator power and load power decisions. The reward function has two layers. A long-term reward separates stable from unstable trajectories. A short-term reward penalizes constraint violations and unnecessary control effort. This design forces the agent to prefer actions that stabilize the grid without excessive intervention. The reward categories correspond to two operator questions. First, did the action keep the system stable after the disturbance? Second, did it do so without violating equipment limits or using excessive shedding and tripping? Reinforcement learning must answer both questions together. The reward design carries the engineering judgment. The Transient Stability Index, TSI, uses the maximum rotor angle separation. A positive value represents a stable trajectory, while a negative value indicates loss of synchronism. Short-term reward is decomposed into energy function, control cost, generator capacity violation, voltage violation, and number of control steps. The energy function terms describe how far the dynamic state has moved from the desired post-fault condition. Cost terms discourage shedding or tripping more than needed. Violation terms punish operating outside generator and voltage limits. The reward, therefore, does more than label success or failure. It teaches the agent what a good emergency response looks like. The TSI term supplies a final stability judgment, while the other terms guide the path toward that judgment. Without short-term penalties, the agent could learn to stabilize by using very expensive actions. Without the long-term term, it could satisfy local constraints while still losing synchronism. The DQN architecture uses two networks because direct bootstrapping can be unstable. The evaluation network estimates Q values for candidate actions at the current state and selects the action with the maximum Q value. The target network estimates the future value used in the temporal difference target. Delayed updates keep the target network from changing at every gradient step. The training table stores transitions in the form state, action, reward, and next state. The TD error is the gap between the target value and the evaluation network value. Backpropagation reduces that gap, so the learned Q function gradually becomes a usable emergency decision rule. The delayed target update is especially useful for power system simulation data, where one action can cause delayed dynamic effects. A slowly changing target lets the network learn from those effects without amplifying every temporary estimation error into a new target. The first case study uses the New England test system, which has 39 buses, 10 generators, and 19 loads. The state dimension is 98, so a simple table-based reinforcement learning method is not realistic. I use neural networks for both the evaluation network and the target network. The parameter table fixes the reward scale. Stable trajectories receive a positive long-term reward. Unstable trajectories receive a negative one, and penalties are assigned to energy deviation, generator action, load action, voltage violation, and step count. These numbers define the trade-off between stability and control economy. A 98-dimensional state includes more information than a hand-tuned emergency rule normally uses. That larger state can capture interactions across generators and buses, but it also increases the need for stable training because irrelevant or noisy variables can mislead the value approximation. The fault scenario is a three-phase fault at the beginning of line 16 to 17, lasting 0.10 seconds, followed by line tripping. Time delay uncertainty is modeled by a normal distribution with a mean of 100 milliseconds and a standard deviation of 20 milliseconds. The reward curve shows learning over episodes. Early episodes fluctuate around low reward because the agent explores many poor actions. Around the middle of training, reward increases sharply and then stays close to the upper level. That pattern means the agent has discovered a control policy that repeatedly drives the system towards stable outcomes under the modeled delay uncertainty. The vertical improvement in reward is more important than the exact episode number. It indicates a qualitative policy change. The agent moves from mostly exploratory or ineffective responses to a repeatable response that satisfies the stability reward and avoids major penalty terms. The Lota angle plots translate reward into physical behavior. Before effective control, several generator rotor angles separate rapidly, a signature of transient instability. After the learned control sequence, the rotor angles remain bounded and move toward a stable pattern. The action table explains the intervention. The first step sheds 70% of the load at bus 28, which is not enough to make TSI positive. The second step trips generator 34, adding a larger corrective action and moving the reward from a negative value to a positive value. The engineering meaning is clear. The agent learns a staged response rather than a single blind action. The staged action also reflects operational selectivity. A load shedding action changes demand immediately, while generator tripping changes mechanical and electrical balance more strongly. The learned policy uses both, but the reward table shows that stability is achieved only after the combined sequence. DQN can overestimate action values because the same network both selects the maximum action and evaluates that maximum. In a noisy learning process, the largest estimate is often biased upward. Double DQN separates those two jobs. The online evaluation network selects the greedy action at the next state, and the target network evaluates that selected action. The equations on the page show this difference in the target YT. For emergency control, reducing overestimation matters because an overconfident Q value can select an aggressive or ineffective control action under fault uncertainty. Double DQN makes the learned policy more conservative in a useful technical sense. In emergency control, overestimation is not a harmless numerical issue. If an action value is too optimistic, the controller may delay stronger action or choose a smaller action than the trajectory requires. Double DQN reduces that risk by using independent evaluation for the selected action. Dueling DQN changes the network representation. A single-stream Q network directly maps the state to Q values for actions. The dueling structure splits the representation into a state value stream and an advantage stream. The value stream estimates how good the current state is before choosing a specific action. The advantage stream estimates how much each action improves or worsens that state. The two streams are combined to produce action Q values. This is valuable in emergency control because many states are obviously safe or obviously dangerous, while only some states require fine discrimination among control actions. The architecture spends capacity on both state severity and action preference. This separation is useful when many actions have similar effects in a benign state but very different effects near a stability boundary. The value stream can represent the overall danger level, while the advantage stream focuses on which action best changes that dangerous state. Rainbow combines several improvements into one agent. Prioritized replay samples transitions according to the magnitude of the TD error. So rare or informative events are revisited more often. The exponent omega shapes how strongly priority affects sampling. Multi-step learning replaces a one-step target with an n-step return that lets reward information travel backward faster through the trajectory. In power system control, the benefit is important because the effect of a load shedding or generator tripping action may appear several simulation steps later. A well-chosen n-step return can accelerate learning without abandoning the long-term stability objective. Prioritized replay also matches the nature of contingency data. Most transitions in a stable recovery may be routine, while a few transitions around instability or constraint violation carry much more information. Sampling those more often improves data efficiency without discarding the rest of the experience. Distributional reinforcement learning changes what the network predicts. Instead of predicting only the expected return, it approximates a return distribution over fixed atoms Z. The support runs from a minimum value to a maximum value, divided into n atoms. The target distribution shifts the support by the immediate reward and discounted future distribution. The KL divergence measures the difference between the projected target distribution and the current distribution. This matters for emergency control because fault outcomes are not perfectly deterministic. Two actions with similar expected reward can have different risk distributions. Distributional learning gives the agent more information about uncertainty in the return. For a grid operator, distributional information is closer to risk assessment. A policy with a high average reward but a heavy tail of bad outcomes may be unacceptable. A return distribution helps the learning process recognize that uncertainty instead of hiding it inside a single mean value. NoisyNet introduces exploration through the network parameters. A standard linear layer computes y equals b plus wx. The noisy linear layer adds a stochastic stream to the deterministic stream using element-wise products with random variables. In early learning, that noise helps the agent explore different control actions. Over time, the network can learn to reduce the influence of unhelpful noisy components. The practical value is that the agent can search for better emergency actions while also becoming robust to phasor measurement unit noise. Exploration is built into the function approximator rather than added only as an external random action rule. Compared with simple epsilon random action exploration, noisy layers can learn how much uncertainty to inject in different parts of the network. That is more suitable for emergency control, where arbitrary random actions during training can be highly disruptive but structured exploration remains necessary. The distributional REBO target combines multi-step learning, double Q learning, and distributional loss. The n-step target distribution contracts the future distribution by the cumulative discount and shifts it by the n-step discounted return. The greedy bootstrap action at the future state is selected by the online network and evaluated through the target network, preserving the double DQN idea. Priority is then based on KL loss rather than only absolute TD error. For stochastic grid disturbances, that choice is useful because the loss can keep decreasing even when returns are not exactly deterministic. The agent learns from distribution mismatch, not just from scalar prediction error. The multi-step distributional target is therefore a bridge between short simulation steps and delayed stability outcomes. It lets the agent connect an early control command with the later distribution of returns, while double DQN keeps the action selection bias under control. The rainbow network architecture adapts dueling DQN for return distributions. For every atom in the support, the value and advantage streams are aggregated, and a softmax layer produces normalized probabilities. The formula subtracts the average advantage across actions, which keeps the decomposition identifiable and prevents the advantage stream from shifting all actions together. All linear layers are replaced with noisy equivalents, and factorized Gaussian noise reduces the number of independent noise variables. The architecture is therefore compact but expressive. It represents state value, action advantage, return uncertainty, and exploration noise in one control agent. The softmax normalization is also important. It makes the output a probability distribution over return atoms, so the network output can be interpreted as a distribution rather than an unconstrained vector. That is the foundation for applying the KL loss on the distributional prediction. The training comparison shows why the rainbow integration is useful. The DQN curve improves but remains noisy and slow. Double DQN reduces some overestimation effects, but its reward still fluctuates for a long interval. Dueling DQN improves representation, yet convergence is not as fast as the integrated method. Rainbow reaches a high reward region earlier and stays there with smaller oscillations. For a stability controller, better convergence is not only a machine learning metric, it means fewer simulated episodes are needed before the policy becomes reliable, and the final policy is less likely to alternate between good and poor emergency actions. The four curves should be read as evidence about training reliability, not as a claim that one architecture always wins in every system. In this fault setting, combining the improvements produces a cleaner reward trajectory, which supports using Rainbow as the stronger emergency control learner. Transfer learning addresses a training efficiency problem. In the pre-training stage, the agent learns an emergency control strategy for a specific fault at an initial operating condition. The experience database and policy network parameters capture useful dynamic knowledge from that task. In the full training stage, a new scenario is introduced and the agent begins from transferred network parameters rather than a random start. The diagram shows the parameter transfer from the first training process to the second. In engineering terms, I reuse what the agent has learned about system dynamics and control consequences, then adapt it to multiple scenarios. This is similar to how engineers reuse studies across related contingencies. A previous study does not solve every new case, but it provides a better starting point than ignorance. Transfer learning gives the neural policy the same kind of head start. The transfer learning case uses 15,143 unstable scenarios and 20,000 training episodes. The reward parameters remain consistent with the earlier case, so the comparison focuses on learning behavior rather than a changed objective. Without transfer learning, the reward curve has deep drops and long unstable periods, meaning the agent repeatedly visits poor policies during training. With transfer learning, the curve rises much earlier and then remains close to a high reward level. That result shows the transferred parameters provide a better initial policy and a better feature representation for the new training set. The comparison also shows why transfer learning matters for scalability. If every fault and loading level requires a long, unstable training phase, building a practical controller library becomes expensive. Faster convergence makes it more realistic to cover many contingencies. The final case study sets the loading level to 106%. A face-to-face fault occurs at 25% of line 5 to 6, and the fault lasts 0.144 seconds. Without control, the system becomes unstable at 2.57 seconds. The learn sequence first trips generator 31 at 1.65 seconds, then sheds 30% of the load at bus 26 at 1.75 seconds. The rotor angle plots show the difference between uncontrolled divergence and controlled bounded motion. The reward moves from a negative value to a strongly positive value after the second action. Timing is central in this example. Both actions occur before the uncontrolled instability time of 2.57 seconds. That leaves enough time for the learned sequence to change the electromechanical trajectory rather than merely reports that instability has already happened. The conclusion is that real-time emergency control can be modeled as a Markov decision process when measurements describe the current dynamic state. The reward must combine long-term stability with short-term penalties for energy deviation, control cost, and operating constraint violations. DQN provides the basic value-based learning framework for a specific fault. Rainbow improves the agent by integrating Double DQN, prioritized replay, dueling representation, multi-step learning, distributional reinforcement learning, and noisy layers. Transfer learning improves training efficiency by moving useful neural network parameters from pre-training to full training. The engineering goal is higher automation and intelligence in grid stability control. My main engineering message is that reinforcement learning is not a replacement for power system physics. It is a way to use physical simulations, measurements, constraints, and stability indices inside a fast decision policy. The physical model still defines what good control means. Thank you for your attention. The contact information and the lab account codes are provided for follow-up discussion. I hope this course has made the connection clear. Transient stability control is a fast physical control problem, and reinforcement learning is useful only when its states, actions, rewards, and training process are designed around that physical reality. For future work, the same framework can be extended by improving state selection, validating policies under broader uncertainty, and testing how learned actions coordinate with existing protection and operator procedures. Those steps determine whether the learning result becomes an operational tool.